Welcome back to the lecture on asymptotics. The first video is going to be on big O notation. So this video is on big O notation and basic properties of big O notation. Asymptotic analysis looks at measuring the resources used by a computation. Two sort of canonical examples of resources that may be used by a computation are the amount of time the computation takes in terms of basic computational steps, and the amount of space the computation uses in memory. As an example, think about multiplying two n-digit numbers using the long multiplication algorithm that many of you used learned in elementary school. And if you recall this algorithm, you sort of write the two, if you're going to square an n-digit number, you write the number down twice, you write it times, draw a line underneath it, and then you start multiplying digits by each other, writing down the products that you get. So the time it takes is the number of digits you have to multiply or add. The space it takes is the number of digits you had to write down on your sheet of paper to carry out the multiplication. So we're going to be generally looking at trying to measure the resources taken by a computation, and we're going to want to parameterize the number of resources it takes by the size of the input we're trying to do the computation on. So just like the example we were talking about a second ago with squaring an n-digit number, we're going to want to know how much time it takes to square an n-digit number as a function of the number of digits in that number, n, or the amount of space it takes to square the n-digit number as a function of the number of digits in that number, n. Great. So the goal for this lecture will be to understand a framework for analyzing and comparing the resource usage of different computations in terms of uh, this function t of n. Great. So for the remainder, for most of the rest of this video, I'm going to be going through some examples on notes. Okay, so we're going to be talking about big O notation. Big O notation is attempting to describe the asymptotics, asymptotic upper bounds on a function. So saying the function asymptotically grows no faster than another function. Great. And so the definition will say a function t of n is order big O of f of n if there exist constants n naught and c that are non-negative such that for all input sizes n bigger than n naught, the resource usage t of n is at most c, a constant c, times f of n. Okay, and so you'll note a couple things about this. When we say a function t of n is big O of f of n, we're saying sort of asymptotically it's upper bounded by some constant multiple of the function f of n. So in particular, we don't care what the function does when n is small. So below some n naught, we don't care what the function does. We only care that after some n naught, it becomes bounded by c times f of n, where c is any constant. We also don't care what that constant c is. Okay, so as an example, suppose t of n is equal to an squared plus bn plus c. Okay, then we might wonder, is t of n order n? Is it order n squared? Is it order n cubed? And again, this should be a review for many of you. So you probably recognize that t of n is order n squared here. But in fact, it's also order n cubed because, certainly a function that grows no faster than than n squared asymptotically also grows no faster than n cubed asymptotically because n cubed grows faster than n squared. T of n is not order n. Great. So let's see how we could argue this very simply. Great. So the first thing I want to do is I want to make the left-hand side of my equation bigger by replacing b times n and c with b times n squared and c times n squared. So because we're looking at non-negative numbers n, we know that as long as n is bigger than 1, and when we multiply b times an additional n, or c times n squared, we're going to make those numbers bigger. So this is for n bigger than or equal to 1. We know that this is less than an squared plus bn squared plus c n squared, right? And now we can factor a plus b plus c n squared. And we realize we can rename a plus b plus c just as some constant d, and so this is equal to d times n squared. Okay, so we see that for n bigger than n naught equal to 1, this function t of n is at least is no more than dn squared. And so d of n, this is order n squared. Okay, and of course, we could do the same trick again where we say, well, this is, of course, less than or equal to d n cubed because we've taken n to be at least n not equal to 1. Okay, and so this is in order n cubed. Great. All right, up next, we're going to look at some useful properties of big O notation. Fact 1 is that big O notation is transitive. Okay, so if f is order g and g is order h, then f is order H. Okay, fact 2. If F is order H and G is order H, then F plus G is order H. In other words, if F grows no faster asymptotically than H, and G grows no faster asymptotically than H, then F plus G grows no faster asymptotically than H. And why might that be the case? Well, notice that, and we'll look at this in detail in a second. But notice that, you know, essentially, if F's asymptotic growth can be bounded by some function C times F H of n, right, and G can be bounded by some other C times H of n, then F plus G can be bounded by the sum of those two constants times H of n. Fact 3. This just is sort of a special case of fact 2, in fact. So if G is order F, then G plus F is order F. Great. And this is, as you can see, just a application of fact 2. Why is this just an application of fact 2? Well, F, so G is order F as a statement of the fact, and of course F is order F. And so now we can apply fact 2 to conclude that G plus F is order F. Great. So I want to go through in detail the proof of fact 2. Okay, and so I just want to write out the assumptions of the fact, which is that F is order H and G is order H. Okay, so F is order H implies that there exists some C and N naught such that for all N greater than N naught, F of N is less than C times G of N. Excuse me, C times H of N. Okay, and we also said G was order H, and that implies that there exists some C prime and some N naught prime such that for all N bigger than N naught prime, g of n is less than c prime h of n. Great. So now what I want to do is I want to combine these two facts we have from the assumption. Okay, and I want to look at for all n that's bigger than the max of n naught and n naught prime. Okay, and we'll call that n naught double prime. Okay, for all n bigger than the max of these, f of n plus g of n is less than or equal to, well, now I'm just going to take these two equations that I have and add them up. Okay, so we know that for n bigger than n naught, f of n is less than c of h of n. And we know that for n bigger than n naught prime, g of n is less than c of h of n. Okay, so if we take n bigger than both n naught and n naught prime, then both these equations hold. Then we can add them together. And we'll get f of n plus g of n is less than or equal to c plus c prime h of n. Okay, and of course this is just some c double prime. Okay, and so we can conclude that for all n naught greater than or equal to, for all n greater than or equal to n naught, f of n plus g of n is at most c prime h of n, c double prime h of n, which is the definition of big O. And so we can say that f plus g is O of h. And that concludes the proof of this fact. Great, so we're almost done with this lecture. I have a couple more things I want to say. The first thing I want to, the next thing I want to say is about using big O. Okay, and I have two main points about using big O. One is you should always be succinct when using big O notation. In other words, we're not going to write things in big O notation that can be further simplified. So do not write things like big O of n squared plus 2, big O of 3n, etc. And why don't we write these? Well, because these can be further simplified, because anything that's order n squared plus 2 is also order n squared. That's much simpler to write, so we should write order n squared. Likewise, anything that's order 3n is also order n. That's simpler to write, so we should always write order n. Okay. The next thing is be tight. In other words, give the tightest bound you could possibly give with big O. Don't give a loose bound when a tighter bound is possible. Okay, so if, for example, t of n is n squared, even though it's true, don't say t of n is order n cubed in your analysis. If t of n is n squared, you should say t of n is n squared. Great. So uh, two things to look out for when using big O notation is to be succinct and to be tight. Okay, don't write stuff that could be further simplified, and don't give bounds that are loose when you could very straightforwardly give a better bound. Great. The next thing I want to talk about is some common runtimes that come up when analyzing computations. The first is order log n or logarithmic runtime. The next is linear, order n. N log n comes up frequently in analyzing the runtime of algorithms that do sorting as part of those algorithms, and probably you've all seen in your data structures class, sorting algorithms like quicksort or merge sort. Order n squared, quadratic runtime, order n cubed, cubic runtime, order n to the k for some constant k, 5, 10, 100, is called polynomial runtime. Order 2 to the n is called exponential runtime. 2 to the n, runtimes like 2 to the n come up, for example, when doing brute force search over subsets. And n factorial runtimes arise when doing brute force search over permutations. Great. So this video has been about big O notation and reviewing some basic properties of big O notation. Up next in the next video, we're going to be talking about exact bounds, lower bounds, and strict bounds.